What if a minefield didn't slow a fleet? It fed it data. The Navy's Barracuda isn't just a neutralizer. It's the pointy end of a network that sees, classifies, and acts before a manned hull gets close. We'll show how AN/AQS-20C sonar cues a semi-autonomous 48-inch munition, why standoff launches from LCS and other platforms change risk calculus, and how DARPA's undersea networking concepts aim to make these drones coordinate like GPS for the deep. If you think this is about one robot, you're missing the system of systems story. Before we move on, please take a moment to subscribe to the channel and like the video. Most people still think of a mine killer as a single disposable torpedo that swims out, touches off, and that's the end of it. The problem with that model is tempo. You clear one, then the next, while a strike group waits outside the cordon. Barracuda flips the logic because it behaves like a node in a larger machine. It accepts work from the network, acts, and frees the network to move on to the next entry without hauling a manned hull into the hazard area. Baseline first, a N/AQS-20C tows through the suspected field and builds a high-resolution map. It flags shapes and highlights returns that match learned patterns. That cue moves across the link to a host, an LCS with the MCM package, or an MCM USV towing the sonar, and the host pushes Barracuda from a safe standoff. The launch point stays outside the mine threat radius, and the neutralizer swims in, so the expensive ship does not. Traditional mine countermeasures put crewed minesweepers inside the mine danger area. That created a conflict between speed and survivability. If you rushed, you risked a hull. If you slowed down, you ceded time to an enemy laying more mines or maneuvering under the umbrella. It was therefore common to pace the operation to the availability of protected escorts and specialized ships, which is precisely what the Navy is trying to unhook. So follow the data. High-resolution sonar returns leave the tow body and get classified on board and ashore using computer-aided detection. The system generates a tasking message that includes location, classification confidence, and approach geometry. Barracuda receives that mission package wirelessly. No tether. It navigates to the target basket, executes its search pattern, performs terminal identification with onboard sensors, and only then commits the kill mechanism. The device itself is small. Length, 48 inches. Weight, 26 pounds. Jet-propelled. It carries a camera and sonar for terminal ID, because in cluttered littorals, the penalty for a false positive is wasted inventory, and the penalty for a miss is an intact mine that delays the lane. A mooring, a rock outcrop, a lost container. These all generate complicated echoes. Terminal sensing resolves that ambiguity at the last 100 meters, so the network doesn't spend two assets on the same entry. Treat the minefield like a spreadsheet. Sensors fill the cells with numbers and tags. Some cells get flagged by the classification algorithm. Barracuda is the formula that runs only on the flagged cells, and it does not recalculate the whole sheet every time. If you sum all of that up, you get predictable throughput from the first tow to the last detonation. This is why the Navy's shift to semi-expendable neutralizers matters. A cheap device that can be thrown at each flagged contact decouples clearance tempo from the presence of a manned sweeper. You don't hold fire waiting for the one ship that can enter the box. You allocate neutralizers until the flagged list is empty, while the crewed platforms stay where their survivability is not at issue. There is also the network angle. Standardized control protocols mean an unmanned influence sweep system, or another USV carrying AQS-20C, can pass a target package to Barracuda without writing custom code for each host. One payload, many carriers, same message formats. Interoperability isn't a press release term here. It is how you prevent the tow body, the classifier, and the neutralizer from becoming a bespoke trio that can't scale beyond a demonstration. So the mini payoff lands cleanly. Barracuda is not the plan, it is the effect. The plan is a data architecture that lets any compatible platform hand it a target at range, then move on to the next cell before the first detonation has even faded. With that local loop closed and repeatable, We can now move on to how the same loop stretches across air, surface, and subsurface into a complete sensor-to-shooter chain. If the sea had a map that updates itself, who keeps the pencil moving? UVS, USVS, or UAVS? The honest answer is all three, and a shore node that acts like the drafting table. Each has a job. Underwater vehicles sense quietly and stay on station. Surface craft tow minesweeping gear and high-resolution sonars. Air systems extend surveillance and provide the fast, wide look, then act as relay towers when the water blocks radio. Shore fusion nodes ingest the feeds, resolve conflicts, and assign tasks so the loop doesn't stall. So the multi-domain picture looks layered. A UUV patrols and records bottom change. A USV carries AQS-20C, or an influence sweep, and does the heavy classification tow. A UAV adds coverage along the route, and when the line of sight exists, it backhauls data to the fuse cell. That cell deduplicates tracks, sets priorities, and pushes a mission package outward. In any case, none of this works if timing slips, because underwater GPS doesn't exist and drift accumulates. That is the tension. Localization and latency break coordination when seconds matter. If a contact's coordinates wander because clocks diverge, the neutralizer swims to an empty patch while the mine sits 20 meters away. It was therefore necessary to treat time and relative position as first-order requirements, not background plumbing. Without them, throughput collapses into handholding and reacquisition sorties. DARPA and BAE systems have explored undersea networking concepts to give UUVSA shared clock and relative position. Think of it as a submerged time base that lets tracks and threats line up across platforms. When one vehicle labels a contact, another reads the label in the same time frame and space frame, so classification and attack orders stay coherent. By this point, you see why the pencil moves only if the rulers match. Interoperability then carries the load from timing to command. The Navy has pushed common control protocols, shared interfaces, and message standards, so a Barracuda task order looks the same regardless of host. One message schema, one set of fields for confidence, approach geometry, and standoff. That means a USV built around minesweeping can still act as a carrier of cues for a neutralizer it didn't originally field, because the interface is not bespoke. By way of example, an ALMDS-like sensor from the air flags a lane with elevated returns. That cue spins the AQS-20C on an MCM USV to classify in detail. Once classification confirms, the shore node generates a target package. A tetherless Barracuda receives it, launches from standoff, and prosecutes. The air asset can loiter as a comms repeater or sweep the next segment, so tempo rises while the link stays clean. Risk calculus improves as expendable or semi-expendable neutralizers absorb danger. Manned hulls remain outside the mine threat radius. You trade low-cost inventory for survivability and speed. And because the messages are standard, you can scale by adding nodes rather than inventing new integration every time you bring a different USV or UUV into the area. Strategically, distributed MCM functions as deterrent near choke points and littorals. The value is measured in hours denied to an adversary and days saved for a transit. In a Western Pacific scenario, speed and survivability matter because minefields can appear faster than manned assets can arrive, and clearance must proceed under threat. It was therefore rational to design a family of systems where a neutralizer is modular and the network decides who triggers it. The mini payoff lands here. The sensor-to-shooter chain becomes platform agnostic. Barracuda acts as a modular effect that any node can trigger when standards are met. By this point, drones aren't replacing destroyers. They're preventing them from being risked, and the pencil keeps moving because the clock and the language are shared. One way or another, that is the shift. Barracuda's value scales with the network wrapped around it. Interoperability turns one semi-expendable neutralizer into a fleet-level instrument because the same task order can flow from air, surface, or shore without translation, and the tempo holds while manned hulls stay outside the threat radius. So the practical cue is simple. Watch for standardization milestones. When control protocols unify across UUVS, USVS, and UAVS, the undersea kill chain stops being a demo and becomes routine fleet work. We can now move on to the constraint set. Next, we'll test how undersea time sync and navigation limits shape what these drones can do beyond minefields.
Signal strike.